Hello there. My name is Brian Reza Smith, and this is going to be the first of a series of lectures to prepare students for their first computer science class. It is a set of lectures that is not going to be enough on its own to prepare you, so I highly suggest you do any extra assigned work or do some exploration on your own. And probably the number one thing I can suggest for any computer science student is to get into a kind of tinkering mentality where you just play around with things until they work. And you learn the most from just going out on your own, adjusting things, doing things like, well, I wonder what happens if I do this. And just through experimentation and trial and error, you're going to figure a lot of things out. So if I could say anything for the very beginning, I would say get into that kind of mentality and it'll take you really far. So the topics for this particular lecture include an introduction to the idea of what computers are, what programs are. We're going to talk about expressions, values, variables, assignment statements, so a lot of these basic fundamental concepts. Furthermore, I want to talk about how to best use these lectures and also some overarching themes that you're going to keep running into in your career in computer science. So first of all, what are we going to do in this workshop, this accelerated workshop? So first of all, we're going to learn and refine our general problem-solving techniques. So as you'll find out, if you're not already aware, a lot of computer science is problem-solving. And everybody's method for solving problems is different. You kind of figure out what works for you and what doesn't work for you. But I would say that solving problems using software is a little bit different than your approaches outside of computer science. And we'll talk a little bit more about why that's so. But we're going to refine your problem-solving techniques. Say you're confronted with a problem, how do I even start? Or if you don't have one in place, I'm going to offer you one that I've done a lot of research and taken from a lot of different sources, and I feel like it works really well for what we're going to do. So that's the first thing, is we're going to learn or refine our problem-solving strategy. Second thing we're going to do is I'm going to introduce what computer science is and a bunch of computer science and programming concepts. And you'll see that as you take classes, you're going to hear a lot of jargon. You're going to hear a lot of these, words that you really won't know what they are, but you'll find out that there's a lot of overlap across your different classes and a lot of different names for the same kinds of things. So seeing that, having a tool belt where you have concepts available, you can go to your different classes and when you encounter a word you don't know, you might do something like, oh, well, that's just another word for this thing that I already know. So I'd like to give you guys a good, strong set of programming and computer concepts so you can go to your computer science classes and have some idea of what they're talking about. Then finally, we're going to practice implementing some of those concepts using a scripting language. And we'll talk about, the reasons for why we picked that. But, like anything, you learn and then you practice. And so we're going to spend some time taking those concepts that we learned and then actually implementing them and actually working them out in code. So besides the three kinds of goals for this accelerated workshop, I'd like to talk about these general themes that you're going to find in this class, but probably in a lot of your computer science classes in general also. So one of them would be this idea of modularity. And what modularity basically means is when you have a very large thing, when you break it into smaller pieces, self-contained pieces, you could think of it from a problem side, but also from a solution side. So we might have a large problem like something like, I want to build a house. And then we can kind of break it into smaller pieces like, well, I need to set up the electrical system. I need to set up the plumbing. I need to figure out the floor plan, things like that. So one of the great parts about modularity, especially within computer science, especially when we start thinking about modularity in terms of solutions, is that we might break our problem or our solution down and realize that we can reuse some of these pieces of our solution. So this is tremendous for the way that we can take very large problems and break them down into smaller pieces. Our code, our actual programming will mirror this kind of problem solving. Like our chunks of code will be modular, like we can move them around like Lego pieces. So really closely related to modularity is this idea of abstraction. And abstraction is kind of, it's not too difficult of a concept, but it is actually an abstract concept in itself. So the best way I can describe it is taking out the details that you don't need to worry about, so you can focus on the bigger picture. So abstraction and modularity are very closely related ideas. So here's an example of abstraction, and then we can kind of bring it back to modularity. Imagine that you are the captain of a spaceship, okay, and your job is to oversee the entire operation of the spaceship, and that includes things like making sure the engine is okay and everyone is healthy and you're traveling to the destination you need to go to and you're following your mission, all these things, right? So in order for you to do that, you don't need to know the ins and outs of how your engine is exactly working. What you would have someone specially trained in order to understand how that complicated engine works. And what you would do is you would abstract out the details and you just say, hey, engineer, is the engine okay? Yes or no? Now notice on your side, you have a very simple input and output. You don't need to worry about all the minute details of the engine. Engine guy says yes or no, and then you can focus on the bigger problem of running the entire ship. So you see how these ideas are kind of closely related, that our engineer might have the goal of understanding the engine as opposed to the whole ship. So that's kind of like a module. And then you're interacting with the engineer. You don't pass all of the details to the engineer about, is the flux capacitor working? Do we have enough fuel? Is, our tolerances are okay? All that stuff is not important. Once we solve the problem of how to, evaluate the condition, the status of the engine, then we don't need to resolve it again. We can just say, is the engine okay? And have that, that module, that smaller Lego piece solution handle all of that for us. And we'll talk a lot about that, but I just want to give you a general idea of that. So that's one of them. It's one of the overarching themes that you're going to see, at least here, almost definitely in all your computer science classes. Another side note about modularity and abstraction is, this is not a computer science thing. I mean, everyone breaks bigger problems down into smaller problems, but really, without being able to do this, we wouldn't be able to achieve all the amazing things we've achieved as a civilization. This is how we can take something really, really complicated and solve it. Solve it piece by piece, each one separately. And you'll see that, as computer scientists, our biggest bottleneck is how much stuff we can fit in our head at any one moment. So being able to take a big problem and break it down and just focus on one piece of it at a time is the bread and butter of doing computer science. Another one of these overarching themes is this idea of sequence. Things are in order. And also deterministic operation. So determinism is it's a philosophical concept. And the word is fancy, but the idea is, that idea of, if you have a pool table and you measure the exact angle of your pool cue, and you have all the angles of the balls and all of that, and the force, you measure the force of the pool cue, you'll be able to predict exactly what's going to happen. So computers, as we're going to use them, follow these rules. They're not magic boxes. Everything happens because something triggered it to happen. And everything kind of happens, everything definitely happens in order. So in a way that this kind of takes some of the mystery out of computers, but on the other side, it makes them much more understandable. So that's something that kind of relates back to this idea of problem solving, that if we're implementing a solution to a problem using a program, we have to think that the computer is going to do things in order. And this gets really rigid because sometimes our brain, we don't really do it like that. Sometimes we kind of bounce around a lot. But the computer is going to do things in order. And also, nothing is going to magically appear in the middle of the operation of the program. So you have to supply every little detail. This becomes kind of tedious. You might say, oh, just give me the thing. There's only one thing in the room. I can't refer to anything else, But for a computer, you'd have to say, give me that red apple that is, at the end of your table. 1 second. Okay, so we had the idea of modularity and abstraction. Those two closely interrelated ideas. We had the idea of sequence and determinism, so things happen in a certain order. We also have this idea that is kind of surprising to a lot of early computer science students, that we're going to focus on problem solving outside of any particular programming language. So a lot of the time, I could imagine you've heard, what's the best programming language, or what's the hardest programming language, or questions like that. And the shocking solution that I didn't expect to find out when I was an undergrad, when I was taking undergrad classes in computer science, was you're going to use a lot of different languages, and you might use whatever your boss tells you to use, whatever your company has already committed to. Or you might use the programming language that is kind of the right tool for the job. So going back to this idea of programming concepts that are universal, that you're going to keep seeing all over the place, computer science is a lot about solving problems outside of any programming language. And just thinking about, what has to happen first, what pieces of information do I need? And so you solve the problem first, and then you can worry about how are you going to take that solution and fit it into some particular language. And you'll see, because programming languages, a lot of them share a lot of the same kinds of components, that's like the big part of our class here, you'll be able to take the same solution and implement it in different languages. So that's another thing that was a bit of a surprise to me. We're going to spend a lot of time solving problems on paper, or, outside of any programming language, and just thinking about, what steps have to occur, things like that. And then finally, the last kind of overarching theme that's you're going to see a lot, and it fits into the idea of sequence and determinism, and this is this idea of input, processing, output. We see it on many different levels. So we see it in terms of the operation of a computer, the way that we interact with it. I type some things in, or I have a video camera. My computer does some stuff in the middle, processes that information, that data, does stuff to it, produces an output. We see it also on the level of an actual program, like our program. You input your hourly wages and your hours worked, some processing happens, and the output is given to you, the amount that you've earned or something like that. And we even see it at kind of the hardware level, at very, very low levels, that there's some input, some work gets done, the CPU does some sort of basic operations, produces an output, and copies it somewhere. So this idea of input, processing, output, you're going to see all over the place. And finally, the last one I do want to talk about is this idea of layers. This idea of layers. This kind of ties a lot of the different ideas, including modularity and abstraction. So when we talk about what a computer is doing, we can talk about it like a program is running, right? Google Chrome or something like that, or my OBS, my open source video capture software. We could just say a program is running. That's true. That's not false, right? We could also talk about what's going on underneath the hood, one level down. We could talk about the program is storing pieces of information. It's manipulating pieces of information. It's scanning through existing information, all kinds of things like that. Then we could talk about even one level down. We could talk about the operating system, or we could talk about the machine itself, the hardware, where there's bits, there are, electrical switches basically that are shooting around and being compared to each other and returning information. So this is another idea, and again, it's very related to this idea of abstraction, that the way computers work, we can think of it like layers, where all of those things are true, right? But they're just kind of different levels of what's happening. That's the last thing I wanted to talk about in terms of our framework that we're going to be doing this entire workshop in. So now we could begin talking about some of the actual content. So the first thing I want to talk about, we're going to talk about computers and programs in general. Okay, so one other thing, if I bump my camera and it looks like a tornado went through here, I apologize. I'm preparing for a very long bike ride and trip, so I'm kind of in the middle of it's pretty messy here, so I apologize beforehand. And another thing is, we go through these slides, I'm going to really focus on some aspects of them, but kind of fly over the other ones for the purposes of time. I want to make this as pithy, as dense as possible. Okay. So one thing that's interesting about computers is that modern computers are different than a lot of the original computers in the 40s and earlier. So originally, computers were only designed to do a single job, and their job was set by the configuration of the actual hardware, the physical thing itself. The instructions were soldered into the chips, or so to speak. They're actually set. Computers these days are different, and they're titled general purpose computers. And if you're curious, look up something called the von Neumann architecture. This idea that the instructions that our computer is running are actually reprogrammable. And this is something we 100% take for granted at this point. So what a program is a set of instructions that a computer follows to perform a task, a particular task. So our computers, we can reprogram them. And that's something that is amazing. It's amazing. In fact, one of the sets of instructions we could give is to emulate a whole other computer, which is totally possible. That's how we could do something like take the idea of a video game system, like a Game Boy or Nintendo or something, and run some software instructions that pretends to be the hardware of the Game Boy or the console. So it's super amazing stuff. So programs are commonly referred to as software. And as we talk about computers, we're going to have this distinction between hardware and software. So if our programs are instructions, I also want to include in software the data that we might have stored on our computers. So you think about, you might have a program, again, that idea of calculating your pay, that has some instructions. Add up all of the, take the times and multiply them by the pay rate, and then for every month add them up or something like that, right? Well, that sounds like a bunch of instructions, but also we have pieces of information there. We have data which are not actions themselves, but they're information. So how much did you make, right? How many different months did you do it? So included in our software would be instructions, but also data. So that's an overview of software. Let's talk about hardware and software. So if we're talking about hardware and software, I think that the hardware is the easier concept to understand. So the hardware includes all of the physical parts of the computer that we can actually touch. So we'll talk about the system itself, but that's just the baseline concept we can work with. So the physical devices that a computer is made of are referred to as a computer's hardware. And a computer is a system of devices that works together. So I don't want to spend too much time on this, but it's worth noting that a computer can really be stripped down to its essentials. And those essentials would be the CPU, central processing unit, and some main memory. We could have a computer that already has some instructions stored in the main memory doing work without any keyboards attached to it, without any network devices to interact with other devices, without a monitor, without any sort of VR headset or whatever. It would still be a computer. So that's something that's kind of worth noting. And we talk about a computer system, just in general, the way that we're used to. We can think of a couple of the main components. So we have the CPU, the central processing unit, which you're going to learn all about in some of your future classes. We'll talk about it a bit, though. We have something called the main memory, something called secondary storage, input devices, and output devices. So input devices, mouse, keyboard, etc. Output devices, printer, monitor, projector, 3D printer, things like that. Then we have our CPU and our main memory. So the CPU, also known as the processor, is this chip that is in charge of actually doing all of these minute calculations. It's actually transforming information, but it works deterministically. Okay, it does work like we feed it this chunk of instructions, fetch information from this place, from this other place, add them together, store the result here. But the CPU is actually the thing that's responsible for doing tons and tons of these little calculations. So our memory would be considered the work area of the computer. And you can think of it like storage. So it is someplace where we can store information, store instructions also for the CPU to run. I want to spend a moment and talk about the hierarchy of storage. And this is an important concept. So let's see here. Okay, so here's our CPU here. And here is our main memory. And here is our secondary storage. Okay, so if you've ever heard of that saying that you're only as strong as your weakest link, that's really going to apply here. And also this idea of a bottleneck. So as you're transmitting stuff from one place to another, and you've got a flow, wherever you're slowest, if you're ever slow in one spot, it's going to slow the whole thing down. That's really true in the hardware of a computer. So I want to use an analogy here, but just another quick aside is just think about if you've ever been on the freeway and you've got 6 lanes across, so everyone's able to move really fast until a bunch of the lanes are shut down and there's only one lane. Well, it doesn't matter that you got 6 lanes across ahead of it. Everyone's slowed down at whatever the slowest part of the entire flow is, right? Or something like that. So here's our CPU here. And this is what's doing the work. So we have this thing called secondary storage. This includes hard drives, flash drives. This will probably be outdated by the time you see this, but it's going to be our storage that is cheaper than your main memory here, but it's also slower. The CPU also has tiny, tiny little bit of storage called registers. And near the CPU chip, there's also this thing called cache storage, but don't worry too much about this. We have this hierarchy, and the goal is to try to get the CPU working as fast as possible. Now, we couldn't work directly, we could work directly from secondary storage to CPU and then back to secondary storage, but secondary storage is really, really, really slow. So what we actually do is we copy everything to main memory. This includes your RAM, your random access memory, and then your CPU interacts with the main memory, does some work, copies it back to main memory, etc. So this hopefully happens fewer times. Let's say we do this 2 times, and then over here, a lot of work happens many times. So this is a vast oversimplification of what actually happens, but the concept is the same. And so if you've ever experienced that phenomenon of your computer taking a long time to boot up, but once it gets going, things are going well, that's because we're copying all of, we have a permanent long-term copy of Windows or Mac OS or something like that. We actually copy all of the operational stuff into main memory, and then from there it can go back and forth to its heart's content. So a really quick analogy about that. And by the way, that's why, at least in the current state of things in 2019, if your computer is running slow, one of the first things you might want to check out is increasing your main memory. And that way your CPU can spend more time working with main memory and less time having to copy over from your secondary storage. So a really quick analogy. So there's our CPU, there's our main memory, there's your secondary storage. Imagine here's my beautiful girlfriend, and she wants to make herself a sandwich. And over here is the fridge, which has all the components for her to make her sandwich. So it's going to be a real pain for her to make the sandwich, going to the fridge and working inside the fridge. That it's not really designed for that. There's no real space for that. So in between her and the fridge is a table, like a kitchen table. And so she can load up on, there's your bread, here is some lettuce, amazing rendition. Maybe I have some, veggie meat or something like that right here. And once she copies this stuff into here from long-term storage into short-term storage, then she just has to make this trip back and forth. I guess she'd be standing right there. And then when she's done, she could take the results and put them in the fridge for later use. So what happens if she keeps grabbing stuff from the fridge? Let's see, what other components? Maybe I need some mustard. So here's some mustard. Let's see, tomatoes. Got a bunch of tomatoes. I don't know. Maybe you get really crazy with your sandwiches. You have a fish. Also have a fish. Sort of a fish. Okay. So now we're out of space in our short-term storage, in our main memory. So what we have to do is we end up having to take this, some pieces from this, copy back to the fridge. So now this space is open, and we could pull whatever else we want and work on it. But you see the problem there is we're interacting with that fridge. It's got the slowest transfer rates, and so it's going to slow down the entire operation. So the better solution would be to expand your table here, and you'll be able to work a lot faster. So that's the general idea here. We're storing our information in a lot of places, and it's got this hierarchy where the fastest transfer rates are the most expensive. So generally we don't have as much storage space there. And so it makes these kind of jumps. Maybe here we would have CPU cache. You don't need to know this stuff for now, and then this idea of registers. But just know this, have this idea that these are the basic overall components of a computer. And in terms of our storage, there's this trade-off of capacity for speed, and it all has to do with how expensive something is. Like if we made our computer, out of only this stuff, it would be unreasonably expensive. Okay, so that's the general idea there for some of the main components of our computer. So you've got your CPU, you've got your main memory, you got your secondary storage. We have input devices and output devices. And that's pretty much it. Okay, let's see. So we talked about secondary storage. So they have those, they're going to be phased out very soon. Those magnetic disk hard drives, they sound like a jet taking off. We also have your solid state drives would be also considered secondary storage. Yep, there they are. USB drives, optical devices, don't really see those as much. And then cloud storage too, we would be thinking of this as secondary storage because it's so far away from the actual CPU, there's a lot of delay in having your CPU access it. So most likely what we're going to be doing, copying from some external storage to something closer to the CPU that's faster. So the same idea. Output devices, okay? Okay, so in terms of software, there's two general categories of software, and this idea is not too complicated. We have our operating system. So we have system software, which is all of the instructions and data that your computer would need to just operate. So if you think about things like an operating system, like Windows, Linux, Mac OS, Unix, things like that. And certain utility programs that are all about just the operation of the overall computer. On the other side, you have your applications. So that includes the things that us at the user level we're going to be interacting with a lot more. So web browsers, games, database and spreadsheet programs and things like that. That relates to this idea of our layer cake. So really quick, so you can think about the operation of a computer like here's us at the top, then we interact with an application, say a web browser. The application makes requests to our system software, like our operating system. Our operating system is actually the thing that is interacting more directly with the hardware. All of this kind of happens simultaneously, right? But we don't see that. That's kind of the magic of abstraction here, is that we've solved all these problems independently, and these different layers communicate with each other in kind of a not too complicated way. But what's happening within one layer is pretty complicated, right? So this just relates to our idea of this layer cake. I wanted to say one more thing about hardware and software before we get on to how computers store data. Actually, it relates to how computers store data. So let's talk about that. So if hardware includes the parts of a computer that you can actually touch, the question about, what exactly is software? Can we touch software? That's the one that's a little bit, that's actually, in my opinion, a little more interesting or just hard to kind of get a hold on. So I have two great analogies for this, and it relates directly to how are we storing information? Where are our instructions and data that we store on a computer? So the first might apply to some of you guys, but maybe not to others, is, have you guys ever seen this toy called an Etch-a-Sketch? So generally, they look like a little screen. They have knobs at the bottom. A lot of the time, the border here is red plastic. Let's see. I don't want to get too fancy with this. This would be red here on the outside. But anyway, the idea is that and this is something that was in the movie's Toy Story. I think one of the characters was an Etch-a-Sketch. The idea is that inside of the Etch-a-Sketch is a bunch of these iron fillings, and turning the knobs takes a magnet and sticks them to the surface, the top of the Etch-a-Sketch. So, meaning that functionally, I could twist the knobs and put my cat's name here, Hairdo the cat. It's the best cat name I've ever come up with. I'm very proud of it. So here I have the word hairdo, but the word hairdo is not permanently a part of our hardware. The word hairdo is there because of a configuration of those little iron filings. And we could easily just wipe it clean and have a different configuration of information that we're storing. Bob Shamrock. That's another cat name. I don't know. It's not my cat name. So in this case, we're also storing some information, right? And again, be thinking. This could be instructions. It could be data. But the word Bob and the word Shamrock are not actually permanently a part of the hardware. They're made out of the configuration of the filings. Now, if that example didn't work for you, we could also just use a playground sandbox where I could take a stick and write out hello. The word hello is not permanently a part of this. And if you think about it, the sand actually is the hardware, right? We could touch the sand, right? But we could easily just wipe this clean also. The information is stored in a particular configuration or the state of what the hardware is in, if that makes any sense. So that's going to relate directly to the next thing we're going to talk about, which is how is information stored on computers? So you've heard that all information, computers work in zeros and ones. You've probably heard of that, right? Now, I want to kind of move away from this idea for a second, where I don't want us to be like looking for the number 0 and the number 1, because really you can think about it more just like switches that have two different positions, up and down. So there I have 1, 0, 1, 1, right? So we don't need to really worry about the physics side of it, where our switches, and by the way, one of these switches, this is the most basic unit of storage, would be called a bit. A bit can either be 0 or 1. But really, we could just think about it like it's either in one position or the other. These have only two settings. Each one of these has only two settings, either up or down. That's it, right? 0 or 1, something like that. So we don't really need to get into the physics of it, where what we're actually talking about is the voltage, right? The electric stuff, you don't need to worry about. You're going to take some physics classes, or you can investigate on your own. It's very interesting, but all we need to be concerned with is the fact that we have these switches, and if you don't want to worry about the physics side, you could actually just literally be thinking we have these switches, almost like a light switch, just up or down. That's it. So this is the very, very basic way that we store all of the information that we're working with computers. All of the things like, images and audio and instructions and raw data of various kinds and text and numbers. All of this is represented with on-off switches. So let's talk about what a bit is for a second. Then we'll talk a little bit more about how we represent numbers, and then also how we represent letters, and a tiny bit about how we could represent something like a picture. So codes are very important. It's inherent in the informal word for programming, coding, right? Codes are very important to computer scientists. And we have codes because we want to transfer or we want to store information, and whatever way we're doing it before has some limitation, right? So you think about codes, we had codes, ancient peoples had codes for things, right? Even pre-language we had codes. We have codes even in our facial expressions, like a smile means I'm probably more approachable than a frown, right? And the important thing about codes is that we have some way to decode them that is agreed upon. So whatever way we take our information and we encode it, we have to be able to have some way to unencode it, take it out, and have it in its original form that everybody agrees upon. So let's talk about something like a traffic light. So I got a traffic light, and I've got 3 different colors. So I've got our green, our yellow, and our red. Now, let's say we were using these on-off switches, and let's use 0 and 1, okay? My question to you is, how many on-off switches, how many bits would I need to represent the 3 different possibilities of a traffic light? So let's say we wanted to store a traffic light. We need to store which color is the traffic light on at any given moment. So that means that we're going to need at least 3 unique codes. Now we can't have the same code for 2 different colors because we won't be able to determine which one of the colors we mean, right? So let's say we tried to represent this traffic light. So we have 3 different settings, right? And we tried to do it with a single bit. So our single bit can either store 0 or 1, right? Well, that only gives us 2 codes. So we're missing one of them. So that's not going to work, right? Well, what happens if we use 2 bits? So let's do this. I'm going to do this branch kind of pattern because I feel like it helps us understand how we can cover all these different codes. So let's say that we have 2 bits. We need to make at least 3 unique codes to represent all 3 colors of the traffic light. Let's say our first bit is 0. What are the total possible codes that start with 0 if we have 2 bits? Well, we have 0, 0 and 0, 1. Let's say our first bit is 1. What are the codes we can make if our first bit is 1 and we have 2 bits? Again, we have 1, 0, and then we have 1, 1. So it takes 2 bits in order to store these 3 possibilities. So maybe we could do something like the code 00 is green, the code 01 is yellow, and the code 10 is red. And then we don't even need this one. That's fine. We can toss it out, or we could do something like we could make an error, error code or something like that. But the idea here, if we were talking about what's the minimum number of bits we would need in order to represent this color, it would need to be at least 2 bits, which gives us 4 possibilities, right? 4 unique codes that we could use. I use this example just to kind of really emphasize that even though we've got these 1 zeros, we can represent all kinds of different things, including, colors. It's just a code, right? We just need to be able to decode it also. So here's another question. How many... So we talked about if I have one bit, let's just say, if I have one bit, here's this column right here is 1 bit, right? I'll do total here. Total codes. So if I have 1 bit, my total unique codes is 2. If I have 2 bits, my total unique codes is 4. Now, what if I had 3 bits? I have 3 of these on-off switches. We're counting what is the total number of unique codes that we could use to represent all kinds of different things. Well, remember we did this kind of branching pattern. If we add another bit to the end, each one of these existing codes would have 2 other possibilities because we're adding on either a 0 or a 1. So here we have 0, 0, 0, and then 0, 0, 1. I bet you're following along. You kind of see the pattern here. I have 0, 1, 0, 0, 1, 1. I have 1, 0, 0, 1, 0, 1. And finally I have 1, 1, 0, 1, 1, 1. So if I have 3 bits, the total number of unique codes that I can make, the total possible things I can represent is 8. Let's see, did I make any mistakes here? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Huh. Interesting little pattern there, huh? So 1 bit, 2 codes. 2 bits, 4 codes. 3 bits, 8 codes. If you can see it, we're doubling each time. And so on. 2, 4, 8, 16, 32, 64, 128. So that's the pattern. So the question is, I have another question for you. Given a number of bits, how many total codes can I make? So if I say we have 4 bits, how many unique codes can I make from that? What's the formula to determine that? Well, we can look over at our table and you can see that if we have 4 bits, we have 16 codes, right? But what's the formula? So let's say given n bits, how many codes? How many unique, let's just say unique codes. Unique codes can we make? Think about it for a second. If you have it, awesome. If you don't worry about it. So the answer is 2 to the power of n. That will tell you how many unique codes you can make given a certain number of bits. And then a little bit of a side note. Well, okay, we'll come back to that. We'll come back to this in 1 second. So this is the basic idea for how we're storing information. Now we can move on to talking about what we're going to store using these on-off switches, these bits. First thing let's talk about storing is numbers. So okay. So really there's infinity different ways that we could count using these on-off switches, because we could decide that 0 means the number 125 and 1 means 2,628,492 and 1, 1, the binary code, we could say this one means 14 or something like that. There's infinite different ways that we can do it, but there's kind of a standard way that we've agreed upon for how to count using just ones and zeros. Binary. Remember, bi means two, like bicycle. So there's a standard way that we've kind of agreed upon. So first, let's take a kind of a step back and think about how are we used to counting, right? So the system that we're used to counting in is called decimal because it's based off the number 10. Deci means 10, like, yeah. And so I want to draw this link between how we count in decimal to how to count in binary when it's all centered around the number 2 because we only have these on-off switches, right? So let's talk about the number 7. No, let's talk about 13. Okay, let's talk about the number 13 in decimal. And from now on, while we're talking about what are called number systems, I'm going to emphasize that we're talking about decimal by putting this little 10 in the bottom right corner. So you can just be thinking, I'm thinking in decimal. So what does the number 13 mean in decimal? Well, we've got our ones place, we've got our tens place, and we have 3 of the ones and 1 of the tens, right? This could be expanded kind of like this, where we say 3 times 10 to the power of 0 plus 1 times 10 to the power of 1. Remember, anything to the power of 0 is just 1. So 3 times 10 to the power of 0 is 3 times 1, which is just 3. Now 1 times 10 to the power of 1 is 10. That makes sense, right? And we could even expand it further. Maybe we say, make this number a little bigger. We'll say 413, right? This would be our 100th spot. So we could make this 4 times 10 to the power of 2. Notice this pattern here that's happening where we start with 0, then we have 1, then we have 2. This pattern is going to be consistent. So now we have 3 times 10 to the power of 0 is 3. 1 times 10 to the power of 1 is 10. And 4 times 10 to the power of 2 is 400. So 400 plus 10 plus 3. That makes sense. You probably remember doing something like this, way back when. It's nestled down there somewhere in the back of your head, I'm sure. Now, let's go back to that first example of representing, well, no. We'll do 13 also, but let's start with something a little more basic. How could I represent the number 5 using binary? So remember, this is out of the question. That would mean that we have more than 2 settings in our switches, right? In binary, we only have 2 possibilities, only 0 and 1. There's no such thing as 5, right? So if I wanted to represent 5, it would actually look like this. I'll do this to put a little, whoops, I actually made a mistake. Nope, that's right. Okay, so that 2 in the corner is to really emphasize the fact that what we're doing here is in binary. You're going to have to shake off all of your instinct that says 101 means the number 101, the quantity that is 1 greater than 100, right? This is not 101. This is a different value. So let's take a look at how we can expand it just like we expanded it for the decimal example. So here, I have, for my coefficient, I have 1 times. Now, instead of using 10 for the base, we're going to use 2 for the base, so 2 to the power of 0. This would be 0 times 2 to the power of 1. Think about, why did I pick 1 right there? It's because of this pattern, 0, 1, 2, etc. And finally, I have 1 times 2 to the power of 2. Well, let's expand this, right? So 1 times 2 to the power of 0, anything to the power of 0 is 1. So this would just be 1. 0 times 2 to the power of 1, well, that would be just 0 because 0 times anything is 0. And finally, 1 times 2 to the power of 2, well, 2 to the power of 2 means 2 times 2. So 1 times 2 times 2 is 4. And that equals 5. So what does that mean? I want to kind of emphasize something here. Let's get rid of 13. Well, we'll keep 13, but right over here. So 101 base 2 is the same thing as 5 base 10. This is kind of a strange thought to wrap your head around here, but these are just two different ways to represent the same quantity. Okay, the quantity is the same, we just have two different ways to represent it. One of them using binary and one of them using decimal. Does that make sense? I hope so. If that doesn't make sense, rewind it, step through it again, or if you need, go to some other resources, but I really want you to understand this. Okay, that reminds me, well, let's do 13 really quick. I find it helps to do a couple examples of this. So how could I represent 13 in binary? So there's 13 in decimal. So in binary, instead of having a ones, a tens, a hundreds, we have more like a ones, a twos, a fours, an eights place. That's what this is going to represent. So there's a couple different ways of converting a number to binary. But one easy method I like to use is find the biggest power of 2 you can that will fit in the number you want, and just start there. So the biggest power of 2 we can fit in 13 would be 8. Then find the next biggest power of 2 you can fit in there without going over. So 8 plus 4 would be 12. And then finally, we're not going to be able to fit a 2 in, because if we have 12 plus 2, it'll be 14. So we can add in this 1. So this here, 1101 base 2, is the same thing as 13 base 10. This is how you represent 13. This is 13, but in binary. And we could expand it if we need. So 1 times 2 to the power of 0, 0 times 2 to the power of 1, 1 times 2 to the power of 2, 1 times 2 to the power of 3. So 1 times 2 to the power of 2 is 1. 0 times anything is 0. 1 times 2 to the power of 2 is 4. 1 times 2 to the power of 3 is 8. So 8 plus 4 is 12. Plus 0 is still 12. Plus 1 is 13. It reminds me of a terrible joke that I have a compulsion. I need to tell it every time people are being introduced to the wonderful world of counting in binary. And the joke goes like this. There are 10 types of people that know how to count in binary. Those that do and those that don't. Think about why that works. If you need, expand this out and you'll get your answer. But I'd imagine almost all of you are groaning, rolling your eyes right now. That's fine. You can pass this curse along to your friends. But I love this little joke right here. All right, so that's what I wanted to say about how to represent numbers. So let's talk about how to represent other things. So let's talk about representing letters. So the computer, remember, the computer has no concept of decimal numbers, first of all. It has no concept of letters or pictures. All it knows is zeros and ones. That's the CPU knows, and that's how the information is ultimately stored. So how can we represent things like the letter A or the letter B? Well, actually, how about let's take a little bit of a backtrack, and I want to ask you, how many bits would I need to represent all the lowercase letters of the Roman alphabet? That means A through Z. So all the letters that we use in English in the Roman alphabet, how many bits would I need to do that? So first of all, we can ask, how many different codes do we need? How many different unique codes do we need to represent all of these letters? So that gets to the question of how many different letters do we have, right? So there are 26 letters, A through Z. So if we need to represent 26 possibilities, how many bits would that take? What's the minimum number of bits we would need in order to represent 26 different unique entities? So think about it for a second. If you need to pause it, see if you can figure it out. I don't need to give you a second because you can just pause it. Well, why don't we just count up from 1 bit until we get enough combinations? You could also do it a different way. Just see what's the largest power of 2 you can get without going over, and then add 1 to it is a possibility, right? So let's say, so with 1 bit, I have 2 possibilities. Bits, codes. 1 bit is 2 possibilities. 2 bits is 4 possibilities. 3 bits is 8 possibilities. 4 bits is 16 possibilities. 5 bits is 32 possibilities. Winner, winner, chicken dinner. You need 5 bits minimum to represent just the lowercase letters in our alphabet. So we're going to have some extras. We're going to have 6 extras. You can do with those whatever you want. But if we need at least, if we need at least 26 unique codes, then we need at least 5 bits to represent that. And then one other little neat aside I want to mention. How can you tell if a binary number is even or odd? Well, let's look at a couple numbers. In fact, let's count. So you got 0, 1, 2, 3, 4, 5, 6, 7. So here is our binary, and then over here is decimal. 0, 1, 2, 3, 4, 5, 6, 7. Well, it looks like our odds are alternating, right? So this would be, I'll put an E next to the evens. Okay, so those are our evens, right? So can you see anything about our odds that would suggest that there's a pattern that you could pick up on in order to determine if they're odd based off of the binary representation? If you think about it, we have 1's place, 2's place, 4's place, 8's place, 16's place, 32's place. You notice that we're always adding in powers of 2. These are all even. You see that? 64, 128. These are all even. So the way you can determine if a binary number is odd is just to look if we've added a 1 or not. You could look at that last digit, that least significant bit, and it'll tell you if it's up, it means it's odd. If it's not, it means it's even. So neat little trick there. Okay, so going back to that idea, we need 5 bits in order to represent the lowercase letters of the alphabet. And let's see how we're doing for time also really quick. Okay, we're doing pretty good for time. We're doing really good for time. Okay, so we need 5 bits to represent the lowercase letters of the alphabet. So we're thinking about, we're kind of moving towards how we can represent letters. Remember, the computer has no concept of what letters are. When I learned about this, I was a little disappointed. Ultimately, there's something called a character set. And when we have our layer cake, here's me, here's application, here is system software, here's hardware. This one has no idea what the letter C is. Has no idea. And actually, your translation from bit codes into your letters is going to happen in the middle here. So there's something called a character set, and this was a little disappointing for me to hear. It was very, very not magical. Is that there's a list. There's basically a dictionary that says letter, code. A, B, C, D, E. We have 1011, 1111, 1101, 1011, etc. Right? So ultimately, what we have is kind of like this. It's called a character set. We just basically have a dictionary where for every entry we have associated with it some value. And actually, the way it's organized is that every letter, every symbol we want to represent, because we need to represent not just alphabet letters, but other symbols like punctuation symbols, math symbols, minus sign, plus sign, operators, things like that. All kinds of different symbols we need to represent. We need unique codes for all of those. Otherwise, it's going to be a mishmash. When we try to pull out all this binary, and we try to, you're writing a letter to your dog, and you're trying to, Dear Fido, you need unique codes for DEAR. They have to be unique, right? Otherwise, it'll get all garbled. So ultimately, it's numbers, binary number, actually hexadecimal numbers that are linked up with the symbols that we want to see on the higher level, human level symbols. So if you're curious about that, I would highly suggest you look up the idea of a character set. Character set. One of the first ones was called ASCII. And this one, every character was made up of 7 bits. How many different unique characters can we represent with 7 bits? That was pretty limiting. It really catered more towards users in the United States. So as we went on, and remember, all of us have to agree that this number means this symbol, right? We can't have any changes. In fact, our standards have to 100% be standardized. We have to agree when we're encoding the information, and then later on when we have a lookup table to pull out the information. They have to link up. So these days, at least now in 2019, we use something called Unicode. And there's I believe that there's an international committee that agrees that all of these number codes mean these specific letters. And there's, I think, the Unicode characters are encoded in 16 bits or 32 bits. So each character, each one of those can have a tremendous amount of possibilities. And that's the way that we could represent not just English letters, not just lowercase, not just uppercase, not just also, mathematical symbols and then punctuation symbols, but every letter in every language, every symbol, every emoji needs its own unique code. So if you're interested in that, I highly suggest you look up something called ASCII, also something called Unicode, and that relies on counting not in binary, but in hexadecimal. And let's see here. I'm going to talk about hexadecimal really quick. Then we'll talk about images, how we could take binary and encode images, and then move on to some of the actual programming concept stuff and less the general computer concept stuff. Okay, let's talk about hexadecimal. So we've already learned that our ways to represent numbers are not confined to just using the digits 0 through 9. We can also use binary, which means we're just using 0 and 1. So remember that if we wanted to represent 13, takes 2 digits. If we wanted to represent 13 in binary, let's see, we had our 8, we had our 4, we had no 2, then we had a 1. Let's see here. 1, 2, 4, 8. So that would be 13. So base 2, 1101 would be the way to represent 13 in binary. So I want to point something out really quick. So first of all, notice that it might take more digits to represent the same number when we have less choices per digit. So in the case that we only have 0 and 1 in each digit, we might need a longer code number in order to represent a bigger number, if that makes any sense. 1 second. In decimal, we only needed 2 digits, 1 and 3, to represent 13, right? So that's pretty neat. And that's a kind of common pattern you're going to see, that our base number, and that's basically saying how many different values can there be in a single digit. In decimal, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In each digit, we can do any one of those. So that's 10 possibilities. And as soon as we want to get past 9, we have to bump it up and add another digit, right? In decimal, we only have 2 possibilities. We have 0 and 1. If we want to add one more than that 1, we have to bump it up and add another digit, right? Okay, so we've seen how we could count in actually any number system we want. And historically, we haven't, as humans, always used the base 10 system. Some civilizations have picked totally different bases for their counting system, and it's totally valid. It's possible. I remember when I learned this, I had this sense that, yeah, you could pick a different one, but why would you? 10 just makes sense. It only makes sense because I'm used to 10. And I'll bet you someone who counted in the base 6 counting system would say, why would you use 10? I have to do all this translation back into the base 6 counting system. So we've seen that we could count in different counting. We have different number systems with different bases, and we could count in all of them. We could represent the same numbers in different in different number systems. So the last one I'd like to introduce you to is hexadecimal, which is another one you're going to see a lot in computers, including in your Unicode character encoding, and also a lot in colors. And we'll talk about why. But the big point here is, if we can store more choices in a single digit, then we could have fewer digits to store bigger numbers. So let's talk about hexadecimal. Now, hexa means 6, decimal means 10. So hexadecimal means our 16 base counting system. So in decimal, we have 10 choices per digit. In hexadecimal, we have 16 choices per digit. Here's an example hexadecimal number, okay? So let's say, well, first of all, let's do a really basic one. No, I'll do something a little bit more complicated. So let's say we have this. This is actually well, first I'll count what are the possibilities in any one digit. So remember, we have 16 possibilities in one digit of hexadecimal. They are as follows: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But in one digit, we can also represent 10. There you see the letter A. That means 10. B, C, D, E. So 10, 11, 12, 13, 14, 15. So including 0, that gives us 16 possibilities in one digit. So you might see a hexadecimal number that looks like this. 1B. We'll do 16 in the corner here. What does this mean? 1B. It is a number, okay? We're representing a number. And let's expand it just like the way we did with decimal and binary. But instead of using 2 for binary or 10 for decimal, we're going to use 16 as the base. So here I have B. B represents 11. So this is 11 times 16 to the power of 0 plus 1 times 16 to the power of 1. 1b is 16 plus 11 is 27. Now, this wasn't that fancy because we swapped 2 digits to represent in decimal would take also 2 digits, right? But let's think about, what if we wanted to store really big numbers with a shorter code, right? Oh, I should have kept that. Let's keep this here. If you could read my writing, you get a, I don't know, some kind of medal. But the idea here is that in any one digit in hexadecimal, we have all of these possibilities, right? That's 9. This would be like our 10, 11, 12, 13, 14, 15. Okay. So, again, what if we want to store a huge number in a small amount of digits? So what if I did something like this? C 4 F base 16. Don't make me do this arithmetic. I get computers to do this, but I just want to illustrate this point right here. So here's F. Let's expand this. This would be 15 times 16 to the power of 0 plus 4 times 16 to the power of 1 plus C is 12. 12 times 16 to the power of 2, which is 256. So here we have 3 digits. 12 times 256 plus 4 times 16 plus 15 times 1. This number is going to be bigger than a 3-digit number we can make in decimal. I think the biggest 3-digit number we can make in decimal is 999, right? So already we have 12 times 256 is going to go way beyond that. So don't make me expand it. Grab a calculator if you want. But the idea here is that if we have more choices per digit, then we can store a bigger number with fewer digits. If you've done anything in web development, if you've ever made a website before, you'll come across something called CSS, which is a programming language, but it's not really a programming language like we're going to use. It more describes a picture, but doesn't do any work. It doesn't do any calculations. All it does is it's kind of like a blueprint. I want to have, a box over here. I want it to be this big. I want to give it this color scheme. CSS is a language for setting the style of your web page. So built within CSS, we have to have some way of representing a lot of numbers. A lot of colors, right? If we're going to be picking the colors for all the text and boxes and borders and all that stuff, we have to have codes for all of these different colors. And the way that they do it, you're going to see something like a hashtag first, 2, 3, 4, 5, 6 hexadecimal digits. So you might have something like FF3, FF3, 7, B, C. I'm not going to decode this, but where we had that whole branching scheme for binary, where every extra bit we added, we're going to multiply another 2. If we're talking about what are the total number of possibilities, 2 times 2 times 2, this would be, if we had 6 bits, if we have 6 bits, we would have 2 to the power of 6. If we're talking hexadecimal now, we have 16 to the power of 6. That's a lot of unique codes that we can use to represent minute differences in colors. And that's the reason why we use hexadecimal to represent colors a lot of the time in computers. All right, now, the final thing I want to talk about representing, now that you know about hexadecimal and you know about binary, and we've talked about representing things in general in binary, then we've talked about representing numbers in binary, then we've talked about representing letters in binary. Let's talk about how could we represent an image. There's a couple different ways to do it, and this is going to be really, really just like a conceptual thing. But think about, if we want to represent an image on a screen, what we actually need to do is we need to set the color of every pixel on the screen. So if we stored things almost like a grid, right? You can imagine like I'm very, very, very zoomed in. We would just need number codes that represent colors for each one of these. And this way, I mean, if we had a lot of these, and don't worry, it's easy for us to store massive amounts of information, right, in binary. If we have color codes for each one of these pixels, that is how we could store pictures and things like that. And imagine if we have movies, we just need to store a lot of these in sequence, have a bunch of these, right? So anyway, that's the general idea for this. You could explore this again on your own, but I just wanted to give you this idea that we could store all of the things that we're all of the information that we're working with in computers is stored ultimately in binary, in these on-off switches. Okay, so let's start to talk about, let's change gears a little bit, and we're going to talk about some of the basic parts and basic concepts we're going to need to be familiar with working with programming languages. And remember, what we're doing is we're giving instructions, right? We need to store information and we need to be able to give instructions. So let's do a little refresher on some of these math concepts. You're going to see that there is a lot of overlap between math and computer science. And there's a lot of aspects of computer science that are basically math, and there's a lot of problems within math that we could solve using computers. There's a lot of overlap. So first of all, let's talk about this idea of a value. So now I'm going to give you a working definition for our workshop, for the purposes of our workshop, but it's not very rigorous or mathematical, and I wouldn't suggest that you go to someone else and correct them and say, no, what a value is actually this. But this is going to be a very working definition for our purposes, okay? So remember that traffic light, oops, that would be green, yellow, red. So our working definition of a value is when we have something that has multiple settings a value is one of those particular settings. So let's say this is the light that's on our traffic light. If I asked you what value is the traffic light on, you could say red. If I asked you what are the possible values the traffic light could be on, you could say green, yellow, and red. And here I might say, instead of something, you might say a category. If you have a category or something that has multiple settings, right? One of those particular settings, any one of those particular settings is called a value, okay? Now, how about this? What are all of the values? List valid values for integers between 2 and 6. And I'll say inclusive. A lot of the times when you hear between this and this, you're not sure to include the actual border values or not. So if I say inclusive, it means that includes those ones on the end. And you're probably familiar with that. So what are the valid values? So here we have something that has multiple settings. Let's list all of the possible settings for this grouping, right? So we have 2, 3, 4, 5, not 5.5. Remember, integers have to be whole numbers, right? So 2, 3, 4, 5, and 6. So those are the valid values for integers between 2 and 6 inclusive. You see here that our concept of a value does not need to be constrained to just numbers. Again, colors, letters, strings. We'll talk all about that. But I want to give this very, very broad working definition for us to be able to move forward from this point, right? Okay. So that's what a value is. Then we have this idea of an expression. And we're going to kind of do things a little bit out of order because I don't feel like there's a perfect way to do this. This one kind of needs two parts. So let's do the idea of an expression. And see if you can remember what an expression is in math. So an example of an expression would be like 7 plus 5, or 1 divided by 2 to the power of 4, or something like that. The idea of an expression is a collection of values and operators. This is the key here, that evaluates to a collection of values. We're going to talk about variables in a second. Variables and operators that evaluates to a single value. So this idea that we have, it's almost like a sentence, right? We have a collection of these values and operators, but the key point is that they can be boiled down to a single value. So when I talk about 7 plus 5 can be boiled down to 12, right? If I have 1/2 to the power of 4, that's 1/16, right? Can be boiled down to a single value. So let's talk about variables next. Now, variables are one of the kind of trickier things that we're going to talk about. Variables and assignment statements they're not bad. but you need to be really solid about them before you can move on. And again, I really want to kind of reemphasize that some of this stuff you may have covered in your different classes, but I want to make sure everyone is on the same page, and I want to kind of give you, in this case, multiple approaches that are all ultimately correct, but maybe multiple approaches can kind of help support each other. Okay. So what's a variable? I want to give a couple different definitions of a variable. Again, let's start with kind of an example. Okay, so let's say I have x stands for 3, right? Or we could say num bananas equals 17. Or we could do something like fname stands for my first name, Brian. Okay, so what is a variable? There's a couple different definitions that we can use here. So one, short and sweet, it's like a nickname. It's an alias. Whoops. It's an alias for some value. So if you look over here, in the future, if I use x, I mean 3. X is just another name for 3, right? That's one way you can think about it. Num bananas is another name for 17. Fname is another name for Brian. So we can think about like an alias, like a nickname. It's a different name for the same thing. Okay? 2. We could say a variable is a value that may change in our solution / program. So I could say num bananas stands for 17, and then later on maybe I'll say, okay, well, I ate one. So now num banana stands for 16. So that's another definition we can use. We could say, one, it's a nickname for some value. Another one, we could say it is a value, right? It's going to stand for some useful piece of information, some data, some piece of information. But this particular setting might change, right? It might be updated at some point. So that's another definition there. It's a value that could change in our program or our solution. If we're not even talking about a programming language, right? We have a variable and just say whatever this thing stands for at this moment. And then the third one I want to use is getting to this idea, kind of going back to the idea of main memory. Let's see, maybe I can zoom out a little. Let's just go to a new page. New. I'm going to discard. Let's see how we're doing for time. Okay, we're doing good for time. Okay, so this third definition. So the first one's like a nickname or an alias. The second one is it's a value that will change, that could potentially change in our program or our solution. And then the third one kind of has to do more with what happens under the hood. So the way main memory is organized, remember your CPU is going to be interacting with main memory, right? So say we have something like this, num bananas equals 17, okay? So this stands for 17. What happens in our computer when we do something like this? So I'm going to give you a very, very generic version. Different systems might do things differently, but it's going to do some version of something like this, right? So your memory is organized into these things called cells. They might be called words also. But the idea is that we might have different binary information in each of these slots. Let's see. Okay, so what happens here when we do num bananas equals 17? Well, each of these slots here, each of these cells, has an address associated with it. Now, this would also be in binary, but for the sake of our example, I'm just going to say this. You can think it's like almost like the address of a house. And so you could see that on the left there, that's the address. On the right is the actual value that's being stored somewhere in our memory, somewhere. So let's say we started out and we did this thing, num bananas equals 17. It means that we want to store this piece of information, this number 17. We want to store it somewhere, right? So what we're going to do is we're going to look for the first open slot that's available. And we're going to associate num bananas. The word num bananas is now linked up with the address 1. So in the future, anytime I want to see what's the value that num bananas stands for, I'm going to look in the address 1, if that makes any sense. And then we're going to store the value in there. So let's see here. So 16, 8, 4, 2, 1. We'll do 1, 2, 3, 4, 5. 1, 2, 3. So next time that I want to change that value, maybe I'll say num bananas equals 4. Again, because num bananas is linked up with the address 1, we're going to change this to 4. Okay, so that's another definition there that is kind of a little bit more nitty-gritty, but ultimately we're dealing with hardware, right? Like that's ultimately what's going on, is there's going to be some association between some name and some address in memory, and then we're going to be updating the value that's stored. That was a lot, okay? But I forgot probably the most important one. Let's see, I don't think I have it anymore because I wiped it clean. But the other really big, kind of the why do we have variables? It's to store some piece of information. We create a variable so that we can store a piece of information in our programs that we're going to refer to later on. That's it, okay? So there's our kind of 4 ways of looking at variables. It's a nickname. It is a value that might change. It's our way to store some information. And finally, we have this name that's associated with an address in memory, and they're bound so that we can look things up. It's kind of related to this idea of storing and updating information. Okay, now I want to talk about I'm going to talk about kind of our typical way of creating a variable and storing a piece of information. But also, I want to talk about what's the difference between a lot of our values and variables. Okay, so remember your variable stands for a value, right? So I want to make a distinction between something called a literal and our variables. So a variable value that may change. Literal is a piece of information that could never change. So some information that literally it stands for itself. Remember, variables may always stand for something else. Stands for something else. Some information can never change, and also always stands for itself. So, example, the number 1. The number 1 would be a literal. We can't say, like with a variable, oh, I want 1 to stand for something else. It would break mathematics if we had 1 and we just said, oh, now 1 stands for this other thing, right? So within our programs, we have these things called literals that they always stand for themselves. They never stand for something else, okay? Variables, let's say we did something like this. Num bananas equals 1. Notice that our variable name is num bananas. We're setting it to stand for this value 1, but we could change it, and we could say now num bananas stands for 2. Okay, this distinction is very important because there are certain things, there are certain pieces of information within our programs that can't stand for something else. Imagine that, everything always stood for something that could change forever. We would never be on solid ground, right? There has to be some terminal point where we say, okay, finally, after all of these links, this stands for this, right? So going back to our definition of expressions, now that we have all of these terms in order, we can kind of revisit expressions. So now, an expression is a collection of literals, operators, and variables. And what was the key feature of expressions? That evaluate, that boil down to a single value. So now we could do something like this. We could say, maybe I want to use a command. Well, let's do a different example. Okay, so anytime we want to, let's do some examples of expressions really quick first. Okay, so let's say we have x stands for 7. Is that an expression? So that would not be an expression because it doesn't evaluate to a single value. We're just saying this thing stands for this thing. It doesn't boil down to a single value. That's a really common misconception. When we're setting the value of a variable, that is not an expression. That's something called a statement. But don't worry about that. Our focus is expressions, okay? So example, so this is kind of to the side. So example expressions would be like 7 plus 5. Remember that one? Boils down to 12. How about 7 plus x? That still boils down to a single value. It includes literals like the number 7 and operators. There's a plus sign. And also variables, okay, fits all those criteria. And finally, yes, it boils down to a single value, 14. So that's also an expression. Now, I did a lot of examples. Oh, here's another expression which might surprise you. 2. So there we have a literal. It's a collection of literals. There's no operators in there. We don't have any operators, but there's a collection of literals. Does it boil down to a single value? Yes. 2 boils down to 2. The most simple expression that we could have is just a single value. That's it. Okay, so now we can get to the next idea is, if we have a variable, how can we fill it with a value? Okay, and this idea, actually, I don't like that word fill, because it's not like that. It's not really like a container that we fill. It's more like we're putting a name tag on it, right? Or we're assigning it a new thing it's associated with, a new thing that's linked together with. So there's our idea of an expression, is a collection of literals, operators, variables. So an assignment statement is our basic way to assign a value to a variable. And our language is really important here. I want you guys to sound competent, and this is the way that computer scientists talk about assignment statements. We're assigning a value to a variable. And the format is almost always something involving an equal sign. In almost every language, it's going to involve an equal sign. But the format that we're going to use in our pseudocode, in our kind of planning phase, and also in the languages that you're going to be probably using, is like this. I'm going to put some brackets around it to indicate that this is like a generic version of it. Variable name equals sign, on this side, expression. So it's very important that you have the variable name on the left. Sorry guys, 1 second. Work calls in the middle of work. Okay, so variable name equals expression. So we could do something like num bananas equals 12. But we could have an entire expression on the right side. So we could say maybe something else. Age, don't ask me why, but we're going to I have this new variable called age, and I want it to stand for how many bananas I have, num bananas plus 4. And this here is an expression, because it does evaluate to a single value. Since num bananas stands for 12, imagine we're doing some substitution here. So this would be 12 plus 4 boils down to 16. So anytime I use age in the future, it stands for 16, unless we update it again. Okay? So this idea that we can create a variable and assign it a value using an equal sign is really, really important. Make sure you get that variable name on the left side. Notice here, if we go back, some of you guys might have asked this question. What happens if I do something like this? Age equals num bananas. Well, because of which side of the equal sign it's on, it'll interpret these variable names in different ways. So for sure, this is going to be the destination. This is where our value is going to go, right? We're not filling num bananas. We're filling age. In this case, what we're doing is we're saying, I have a new variable named age, and I want it to stand for... Now here, we're not going to use the variable name. We're going to use the value it stands for. You can always remember that whatever happens on the right side... Oops, too far. Whatever happens on the right side of an assignment statement has to actually be some piece of information, right? It has to get us to some actual value somehow. So if we use a variable on the right side, we mean its value. We mean the setting that it's on, right? The variable on the left side, that's like our destination, the thing that we're, quote unquote, filling. Now, going back to this, numbananas plus 4, another detail about assignment statements that might be confusing, unless you catch it right at the beginning, which we're doing, is this idea that we're going to evaluate this first before we give this value to age. So we're going to do all the calculations we need to do to boil it down before we assign that value to the variable. That's very important. So in case you're wondering about the sequence of steps that happens, we have to give age a single value. It has to stand for something. And in order for that to be true, we need to evaluate all the stuff on the right first. Okay, I hope that makes sense. Now let's see here. Now we're almost done with, let's see what we're doing on time. All right, so we have 9 minutes left for this first workshop. I want to talk about two things. We're going to go a little bit over 9 minutes, but I want to talk about two things really quick. So first is this idea of data types. And then second, I want to actually play around and create some variables in JavaScript. So we've talked about how we could represent different kinds of information in our programs, right? Computers ultimately can store everything in binary, but at a higher level, what we're doing is we're dealing with all kinds of different kinds of information. Our programs might process words, might process numbers, might process images, any kind of information that we want. We're going to be dealing with it, right? So in terms of the way that we're going to be coding, I want you to always be thinking about what kind of information we're dealing with. Imagine, we have some program that is going to tell you how much tax you owe based off of your state. Please enter state in letter code. So if you're from California, CA or Alaska, AK or something like that, right? So it might be very important that our input information is letters and not numbers, right? If someone plugs in, 59, our program will not work. So we have to have some distinction between the kinds of information, the kinds of data that we're going to be working with. That's really important. So in a lot of languages, you're going to specify what kind of information your variable is made to store, basically. So in languages like Java and in C++, you create a variable with this format. So this is called declaring a variable when you create a variable. And then we also have assigning a value to the variable, which is, setting what does it stand for, right? So if you want to create a variable in Java, you do something like this. Data type first, and then variable name. So, for example, if I wanted to store my age as a whole number, as an integer, I would do something like this. Integer, age. And then after I created my variable, I could do something like age equals, how old am I? I'm in my 30s. So age equals 35. This is one of the first times that we can start to see that sequence is very important. I can't do that first. I wouldn't be able to say, take my variable named age and set it to 35. Okay, now create a variable of integer type called age. That would not work. So this is one of the first times you can see that the ordering of things is really, really important, right? We can't skip these things. Now, different languages handle this in different ways, but in general, for our class, this is going to be the way it's going to be. So now, there are a couple different data types that I want you guys to be familiar with. So, because we're going to be working in JavaScript, I'm going to make, so on this side I'll say general category. On this side I'll say JavaScript. So, in general, across many languages, there are number data types, so our variables, our values. Ultimately, it's our values that we're storing, and the way that the particular bit codes that we use are going to be different depending on what kind of information, what data type we're storing. But in general, we have numbers. So, example, 3, 4.2, 0.001. -5, etc., right? Then we have character data. Examples, the letter B. Maybe we have a string, like a collection of multiple characters. So, Brian. And then here is something that's kind of tricky, but I want to be really clear about it. We might have this character value 7, which is not a number, so we can't do math with it. But if you think about, if we think about the name Route 66, the famous highway that stretches across the United States, Route 66 is just a name. 6 is just it's a name part, right? So we can't do math with it. That's an important distinction here, right? Now, different languages are going to handle this in different ways, and as you'll see when we get to JavaScript, it does some really weird things with it. But so we have numeric data, we have character data, we have Boolean data. So the Boolean data type was created when we want to store, remember, this all has to do with we're storing some piece of information, right? So in the number data type, we're storing some quantity of something. In the character data type, we're storing words, names, things like that, right? In the Boolean data type, it's there when we just want to store something that only has 2 possibilities, okay? And a lot of the time, this is going to be either true or false. Something that's kind of strange is that this true is not going to be like our character version of the letters TRUE. It just simply means the switch is up or the switch is down. It's kind of like binary, but this idea that we have some data type, some way to store a piece of information that only has 2 possibilities. For example, if I was programming a game and I wanted to store whether my character can swim or not, I might store it in a value called, in a variable called can swim. I might do something like this. Boolean variable, whoa, where did that go? Okay, so Boolean can swim equals false. So now in the future, if I talk about can swim, or here, I actually combine that in 2 steps. Boolean can swim, and then can swim equals false. So can swim stands for the value false. And then, maybe I take some swimming lessons and then we could change it to true. So for the majority of what we're going to be doing, we're going to be sticking to these three general types. Okay, and JavaScript has numbers, characters, and booleans. It also has a couple other types, which when we get to it, we'll talk a little bit more about. But this is really to limit, our domain of the things that we're focusing on. This is really what we're going to be focusing on. Now, in Java, make another category here for Java. So there's a number in JavaScript. In Java, there are many different data types to represent different kinds of numbers. Integer, something called a double, even byte is a number. Let's see here. Int, double, float. So these are to represent different kinds of numbers. We have unsigned, integer. So we might want to store only positive integers. Well, we could use less bits to store that information. Or we could store a bigger positive integer if we use an unsigned version. Anyway, that's something we don't need to be concerned with. In JavaScript, there's just numbers, and that will include all negative numbers, all decimal numbers, all integers, all of that stuff. Makes it kind of easy for us. But I want you to be aware that in the future, if you use a different language, it might be more strict about the kinds of values that we could store in different kinds of variables. And that there is a huge distinction between something like 7 and something like 0.4 and something like negative 52. There's a huge distinction between these, and they're actually represented using a different scheme of bit codes for each of these. That's why it's really important. Okay, so just be aware of that if we're dealing with information, it's always important to remember what's the data type. What type of information are we working with at any moment? And remember that an assignment statement is our way to assign a value to a variable, and it has that variable name equal sign expression. It's always the case. And let's see here. Types Boolean. We could do a little Boolean logic later. All right, last thing I want to talk about before the end of this session. Let's play around with do a little bit actual coding. So the reason that I use JavaScript is because it's so easy to get up and running. And remember, there's this idea that programming languages have a lot of the same components across the languages. So for now, we're just going to pick a language and we're just going to get familiar with these general concepts. Learning about how to take this solution and implement it in a different language is really actually the easy part. It's not the language that's the hard part, it's the solving the problem that's the hard part. So we're just going to stick to JavaScript for now. You may encounter other languages in the future, but the more familiar you get with a couple languages, then it becomes really a cinch, just moving from one language to another. So I picked JavaScript because we can easily do some JavaScript in any web browser. We don't need to set up any special environment to work in. So I want you to open up a web browser. If you could use Google Chrome would be optimal. But if not, you might have to do things a little bit differently. Almost every web browser has this, though. So what we're going to do is we're going to open the developer's tools for the web browser. So I'm going to right-click on the background, and I'm going to click Inspect. Now across the bottom here, you see we have these tabs. I'm going to click this one that says Console. And ignore this red stuff here, don't worry about it. Now this is pretty neat. Ultimately, if we're writing some JavaScript, I forgot to give a little history on JavaScript. It's a very simple language that's made to automate web pages. It's not really a language that's made It's made to be a language that people could just pick up. That's why it's great for us. And you're going to use many different languages in the future. So ultimately, if we're going to be actually storing a program in JavaScript, we want to store it in a file. It might be huge, right? It might be like hundreds and thousands of lines or something like that. But we could also open this console here and just type lines of JavaScript and just see what it does. Now, I want to remind you of this concept of input, processing, output. And you're going to see that that's exactly what we're doing here. So why don't we try plugging some input into JavaScript, see what processing occurs and what output JavaScript gives to us. So let's start with the basic. What happens if I put in a literal value, 7, and I hit enter? Let's see if I can make this bigger. Yes, I can. Oh, I wonder if my face is covering this right now. Ha! Okay, my face is covering this. Let me move it over here. All right. So I hope you can see here in the bottom right corner, when I plug in 7 and I hit enter, the output is 7. So we're basically saying, I want you to evaluate this. Here, I'm going to give you some code. Do whatever you can to condense it, to evaluate. Give me the single value that's the output. And you remember the most simple expression we could have is just a single value, a single literal will just give us that single value, right? Well, how about 7 plus 5? That gives us the output 12. Okay, so great, glorified calculator. Not much, right? But this is the building blocks of what we're going to be doing. So how about something a little different? Let's try creating a variable and storing a value. Okay, so I'm going to use the keyword var. There's many versions of JavaScript that have been merged over time, so there might be actually multiple ways to do the same thing. For what we're doing, I want you to use the keyword var to really specify you're declaring a new variable. You're creating a variable, okay? And let's try our old pal num bananas. So there's var num bananas. So I created a variable called num bananas, and notice the output was just undefined. It doesn't really have any output for that. We're just saying, hey, I created a variable. It's not like, oh, the answer is 15. It's just like, okay, you created a variable. You declared a variable. Now that I've created the variable, I could do num bananas stands for 17. So here's our assignment statement, right? Okay, num bananas stands for 17. Is that okay? We got 17. Now, what happens if I do num bananas plus 2? Num bananas plus 2. Well, that's an expression. I got a variable. I have an operator. I have a literal. We have that number 2. And the evaluated form is 19. Something else I want to show you. So notice that we had 2 steps when we had our variable. First, we declared the variable using the keyword var. Var is a very special word. We could never create a variable called var. Let's see. I'll bet you it's just going to say, you can't do this. Right. You can't do that. Var is a restricted word. We cannot use the word var when we're creating a variable. Okay. So var is a special word that just says, I'm going to create a variable. So we did it in 2 steps before. First I said var num bananas. By the way, I'm hitting the up arrow key and down arrow key to go up and down. Var num bananas. And then the second line, I assigned a value to it. Num bananas equals 17, right? Well, you could do all of this in a single step. So I'm going to say var age equals 35. So check that out. I'm doing 2 things in one line. Var age is going to declare a variable, create a new variable called age. Then I'm also assigning the value 35 to it. And why don't we get a little crazy here and even include a +1. So we're using the correct form for our assignment statement. Variable name equals expression. Why not? Num bananas. All right, now let's see. What is age? 52. I got old. Don't eat too many bananas. They'll get old fast. So that's a form I want you to get used to. It'll make things a lot faster. If you feel more comfortable at first just creating your variable and then assigning a value, that's fine. But you're gonna be doing both of those in the same line really fast. Okay, now going to that idea of type, there's also a keyword called type of. You could do type of and plug in something, some value or variable name, and it'll tell you what type it is. So if I do type of 7, it tells me I'm dealing with a number. I think I don't want to go too much more into it than that. Let's do this. Type of, do you guys remember we had numbers, we had character data, and in JavaScript those are called strings. We also have the third one. What is the type of true? Output is Boolean. So how about this one? What is the type of quote marks around TRUE? So quote marks around it forces it to be a string. We're not talking about the Boolean version. We're talking about just the letters TRUE. We're not talking about an on-off switch. We're literally talking about TRUE. So that would give us string. And then, just once more, to really drive home this point, what if I do type of quote marks 66 string? Okay. So that's it for today's lecture. If you have any questions about this, feel free to contact me. And hope you have a great day, and I hope you play around with this a little bit. Here, I'll give you a little something to pique your interest. We could do expressions that evaluate to numbers, 7 plus 5. We also have expressions that evaluate to true or false values. So, is 7 less than 10? True. Is 7 greater than 10? False. True. Well, we'll get to that soon. All right. Enjoy.